Remember from introductory chemistry, we defined something called the reaction quotient, Q, and Q was essentially the equilibrium constant, except that you weren't using equilibrium concentrations, you were using the concentrations at some particular time. This capital Pi means products, so this means take the product of the products. Oh, weird. So this means take the first product, the second product, the third product, you multiply them together. It's like the sum, the sigma, capital Greek letter sigma, meaning sum. This is capital Greek letter pi, meaning product. So anyway, maybe you want to refresh your memory, or maybe remember that. So what we're going to do here is to get a bigger understanding, or better understanding, bigger understanding of what the reaction quotient means. Let's take a simple reaction. We'll do a gas phase reaction. A, that's the stoichiometric coefficient. This will be in the gas phase. Will be in equilibrium with B, stoichiometric coefficient B times molecule B, again in the gas phase. Let's look at, say, the free energy change for this reaction. Well, from our previous discussion, this would just be the stoichiometric coefficient of B times the chemical potential of B, number of moles of B times the chemical potential of B, minus the number of moles of A times the chemical potential of A. That's what delta G of a reaction will be. We also know that from our previous discussion, mu A, the chemical potential of A, will be the chemical potential of A at some standard state, and since this is a gas phase reaction, the conventional standard state will be 1 bar plus RT times the natural log of the pressure of gas A. Let's assume ideal, so we don't have to worry about fugacity and fugacity coefficients. We can write a similar equation for mu B. That will be equal to the standard chemical potential. That'd be the chemical potential 1 bar plus RT times the natural log of the pressure of B, assuming again ideal, over this reference pressure. Note that this pressure here, that 0, corresponds to that. And by specifying a reference pressure, usually it's units of 1, you specify the units of the pressure you actually measured. So for example, if P0 is 1 bar, that means that the pressures you measure of A and B have to be in units of bar, because you want the units to cancel out, because you have to take the logarithm of something that does not have any units. So by specifying the standard state pressure of 1 bar, we are specifying what units we have to measure pressure in. That's a concept that was sort of introduced in Intro Chem. Remember, you said, well, we'll plug this into the equilibrium constant, but the concentrations will be, solution concentrations will be 1 molar, and the pressures will be 1 atmosphere. What that corresponds is that the standard state is 1 molar for solution. Standard state is 1 atmosphere. So just remember that. Okay, that's just an aside. So now we're going to use the delta G for the reaction using this. This will be B times the chemical potential of A, B times the chemical potential of B, there it is. So I'll just write that here, plus RT times, this is a gas phase reaction, so pressure of B over pressure, standard state pressure, so the pressure of B has to be in a bar, minus A times the chemical potential of A, that's the standard state chemical potential of A, the chemical potential at 1 bar, plus RT times the natural log of PA. The actual pressure of A, which is the viscosity because we have an ideal gas. Now let's rearrange this equation a little bit. Let's call this B times chemical potential of A minus A times the standard state chemical potential of A. So I took that term and that term, put them over there, and then this will be B RT natural log of PB over P0 minus A RT times the natural log of PA over PA0. So let's continue on here. Let's call, say, B mu A0 minus A mu, B mu A0. Let's define this as delta G0, the standard state free energy change Remember, this is the general equation for free energy changes. So if we just put a 0 there, 0 there, we'll put a 0 there. So there it is. Yeah. So that's the free energy change when the compounds are in their standard state. And we have like B RT natural log of the pressure of B divided by the standard state pressure. We can rewrite that as RT times the natural log of the pressure of B over the pressure of standard state pressure raised to the A power. Raised to the B power. Write the same thing. Say we have A RT natural log of pressure of A over pressure, standard state pressure. That would be just RT natural log of the pressure of A over the standard state pressure raised to the A power. This was raised to the B power. So putting all those together, these manipulations here, and using that symbol delta G to represent that, what we end up with, okay, so we're going to rewrite this equation. We made a different symbol there. We put the B up there, put the A up there, and that power. So what we end up with is a delta G for the reaction is delta G0 plus RT natural log of PB over P0 raised to the B power minus RT natural log of pressure of A over the standard state pressure raised to the A power. And note that minus there, you just flip these around. So this can be written as delta G0 plus RT times the natural log of PB over P0 raised to the B power over pressure of A divided by the standard state pressure raised to the A power. Oh, look at that. This is kind of cool. This is, as we defined it in Introchem, Q. It's the, in this case, gas phase, the pressures raised to the stoichiometric coefficient of the products. This is the products. And here's the pressure raised to the stoichiometric coefficient of the reactants. And that ratio is Q. What is different from introductory chemistry is now we're dividing these pressures by the standard state pressure, so that this whole thing will be unitless when you take the logarithm. We have to take a logarithm of a number rather than something that has units. It used to be we just sort of threw that out there, and in Introchem we didn't put P0 there, we just said standard state, blah, blah, blah. Now we know explicitly where that standard state comes from. It comes from, well, we're just defining a standard state, and we're measuring all chemical potentials and all free energies from that standard state. In this case, that combine everything, so delta G, the reaction, is delta G0 plus RT times the natural log of Q. So there we go. That's something you're just throwing out there in Introchem. Now we know a little bit more about that. And here is the more general case, where you have more than one reactant and more than one product. You just multiply them together, making good progress. So now let's look at equilibrium. Now that we know what Q and K are, or well, we actually don't know what K is, but let me define at equilibrium, K will be defined as Q. So this Q is at equilibrium. So at equilibrium also, delta G is equal to 0. Remember, you have a minimum free energy, so it's not changing. The derivative, the slope is 0. So this means that 0 is delta G0 plus RT times the natural log. We're going to make this switch in symbol from Q to K, or in other words, delta G0 is minus RT times the natural log of K. And delta G0 would be the free energy change when you start with reactants and products in their standard state and let them react. That's kind of cool. Well, that ends it for this first part of the lecture, and we'll continue on in a little while to the second part of the lecture.